This week, we'll discuss regression analysis, which is a general method for finding relationships between different kinds of data. Recall from basic algebra that a linear equation is a special type of function y equals beta 0 plus beta 1 times x, where beta 0 is the y-intercept, or just intercept, and beta 1 is the slope. An example of an exact linear equation like this that we find in the real world is the relationship between Celsius and Fahrenheit. F equals 32 plus 9/5 of C, where beta 0 in this case, the intercept, is 32, and beta 1, the slope, is 9/5. This relationship is purely deterministic because any given value of C will consistently result in the same value of F every time we plug it into the equation. For example, if we plug in 0 degrees Celsius, we will always get 32 degrees Fahrenheit. And if we plug in 20 degrees Celsius, we will always get 68 degrees Fahrenheit. Because we get the same value every time, this type of deterministic relationship is not usually of interest to us in statistics, where we're concerned more with random relationships between different quantities. What we often find in the real world is that two quantities may have an underlyingly linear relationship, but there's some random noise, which we represent with epsilon, that causes the y values to deviate from the line. Thus, for some particular x value, we might expect y to have a particular value due to an underlying linear relationship, but the random noise causes that y to be a little higher or perhaps a little lower. Crucially, that random noise, that variation from the underlying abstract theoretical linear equation, is completely unpredictable and can vary with any choice of x or y. So we never know for any particular point on this line whether there's going to be variation upward or downward, or how big that random noise will be. That is, how far away y is going to deviate from the linear equation. In cases like this, we can perform what is called simple linear regression, where we use the equation y equals beta 0 plus beta 1 x plus the random noise epsilon, and we assume this as a model and check for goodness of fit for this model to our data. In simple linear regression, beta 0, the intercept, is sometimes called the regression constant, and beta 1, the slope, is sometimes called the regression coefficient. We also usually refer to x as the independent or predictor variable, and y as the dependent or response variable. This is because we usually suspect that there is some causal relationship between x and y, such that a change in x causes a change in y. However, if x and y have a linear relationship, then whether we have x as the independent or the dependent variable, we still have a linear relationship. Thus, the underlying mathematics will be the same regardless of whether x or y is our independent or dependent variable. In R, we can implement simple linear regression with a combination of two commands, lm and summary. And from this, we can calculate beta 0 and beta 1, as well as a p-value for a hypothesis test, testing to see whether the slope beta 1 is equal to 0. If beta 1 equals 0, then the regression equation loses its linear relationship and we just get a flat line with only random noise. Thus, the relationship between x and y would be purely random. So we want to reject the null hypothesis to prove that beta 1 is not equal to 0, and thus that there is a genuine linear relationship beyond simple randomness. These commands can also give us a special value called the coefficient of determination, abbreviated R squared, which is a measure of how much of our data, how much of the variation in our data is explained by the simple linear equation y equals beta 0 plus beta 1x without the random noise. When r squared is close to 1, this means we have a good model for our data. It's a good fit because most of the variation is accounted for by that model. When r squared is low, that means our model is not a good fit, that there is a lot of variation not accounted for by our model. To use the lm command in R to perform simple linear regression, we need two vectors of data. This must be paired data, a y vector for our dependent variable, and an x vector for our independent variable. This will be written lm parenthesis y tilde x. Note that y and x are, of course, arbitrary names for these vectors. They could have any name we want. So we could perform simple linear regression on vectors with names such as duration and intensity, or f1 and f2, or any other names that we want for our two vectors. It's important to remember that y and x must be paired data, which means we're taking two measurements for each individual that we have access to. For example, if we're measuring f1 and f2 for vowels, then we need to measure f1 and f2 for each vowel. And these values need to be listed in order and matched up appropriately in y and x. So for example, the first vowel that we measure, f1 and f2 will be the first measurements in y and x. The lm command will give us a lot of information about the linear model used to describe the relationship between y and x, but often we're only concerned about the regression coefficients, the intercept and the slope. To get those, we can use the suffix $coefficients, or shorten it to just $coef. The output of this command will be a vector containing two values. The first is beta 0, the intercept, and the second is beta 1, the slope. Together, these give us a linear equation that is the best model that we can find to fit the data that we have, assuming that it has an underlyingly linear relationship. But how good is that model as a fit for our data? This is where the summary command comes in handy. The summary command is rather different from other commands that we've seen. It takes as input a model. So in order for this to work, we have to use summary, parenthesis, then lm, and then the data that we wish to compare. The summary command gives us a lot of information about the nature of the model inside it. But there are really only two pieces that we are concerned with here. One is the p-value for testing whether beta 1 is equal to 0 or not. That is, whether y has a linear or random relationship to x. The other piece of information that is of interest is the r squared, the coefficient of determination, which tells us what percentage of the variation in our data is accounted for by this particular model. These two pieces of information can be obtained from the summary command using suffixes. For the p-value, we have to use the unfortunate $coefficients bracket 2, 4, or shortened coef bracket 2, 4. And to get the r squared coefficient of determination, we use $r squared. In addition to this information, it is often useful to look at a plot of your data. The plot you see here is a scatter plot, which is a special type of plot that is often used when looking at relationships between two variables. To create a scatter plot, we use the command plot, and it can take a relationship of the same structure that we used for the lm command, in this case y tilde x. The result will be a plot in the lower right pane in RStudio with a bunch of dots showing each of the individual points in your paired data. You can also overlay the regression line from a simple linear regression by using the AB line command. It takes a linear model as its input, in this case, lm parentheses y tilde x. Running these two commands one after the other will thus give you a scatter plot of your data with a regression line running through it. Here we see 6 different such combinations of scatter plots and regression lines for 6 different sets of paired data. In each case, we've also calculated the R-squared and p-values for the relevant linear models. In the top 3 cases, we see that p is less than our usual 0.05. This means we can safely reject the null hypothesis that beta 1 is equal to 0. That is, in these 3 cases, y seems to have a genuinely underlying linear relationship with x. In the bottom 3 cases, however, p is greater than 0.05, which means we fail to reject the null hypothesis, and therefore we can't determine that y has a linear relationship with x. It seems to be purely random. There are many reasons why we might get a p-value that is too high. Perhaps the slope is too shallow, or maybe there's too much variation in the data, or a combination of the two. Note that in all of the 3 cases where it's a random relationship, the R-squared value is also fairly low. This makes sense. If we can't prove that there's a linear relationship, then it doesn't make sense that a linear model would be able to explain very much of the data's variation. So in the bottom left, we see that R-squared is 0.0377, which means a linear model can only explain about 3.77% of the variation in the data. That's not a lot. However, in the top 3 cases, we see that the R-squared values are higher, and in some cases, much higher. For example, in the top left, we have an R-squared value of 0.3535. That means about 35% of the variation in the data is explained by the linear model. This still leaves about 65% of the variation in the data unexplained by a linear model. It could be purely random, or it could be explained by other factors that we haven't considered. Regardless, it seems like we have sufficient evidence to believe that there is some linear relationship between x and y. If we consider the data in the upper right, we see that the R-squared value is somewhat low. Only 9% of the variation in the data is explained by the linear model. That leaves 91% of the variation in the data that's still unexplained. However, we still have a significant p-value here. Therefore, there is some underlying linear relationship. An important piece of these plots to pay attention to is the white space, how much of it there is, and where it's located. In the upper left data, we see that there is a large amount of white space, and that white space is in opposite corners. This is a strong indication of a low p-value and a high R-squared value. In contrast, for the data in the bottom right, there's basically almost no white space at all. This is an indication of a high p-value and a low R-squared value. Regression is actually a general method that goes beyond simple linear regression. You can have equations with multiple variables, nonlinear equations, and even variables that aren't continuous or even numeric. All of these methods beyond simple linear regression are beyond the scope of this course, but you should read up on them in the class notes and beyond if you're interested.